Now we'll talk about some more addressing modes. They are displacement modes. Okay, so there are three different addressing modes which comes under this displacement mode is index register addressing mode, base register addressing mode, and PC relative mode. These are popular. Of course, there are some other variations also, but I am not discussing. These three are sufficient. So what is index register addressing mode? I will explain you. Similarly, you can understand base register and PC relative. Though the names are different, but they are almost same. Okay. Now to understand that, you should understand a concept called effective address. So what is all about this addressing modes? This addressing modes is all about how you represent operand, right? How to get the operands. So that's why I can say that finding the operand is important, right? In all the addressing modes. Let us talk about, that's why, a concept called effective address. So finally, effective address is nothing but address of the operand. Example, let's say you are using immediate addressing mode. In that, what is the effective address? Where is the operand? Directly we have. Are we specifying any address of that operand? No, directly we are giving the operand. Then what is the purpose of effective address? So effective address is not defined for immediate addressing mode. So let us ignore that. Now we'll get one more addressing mode, that is register addressing mode, correct? In register addressing mode, where is the address? Where is the effective address? Effective address is nothing but, example, in the register addressing mode, you write like this, right? At R1, R2, R3. Let us take Ri, okay? So, where is operand? We have operand in R2 and R3, right? So, that we are going to add. So, how to get R2 and R3? I mean, how to get operands here? So, effective address here is nothing but directly, so register R2, correct? R2 is the address of the operand. So, that is very easy. Now, we'll see direct addressing. In absolute, otherwise in direct addressing mode, we have instruction like this, right? Load R1 and something A. We have written this kind of instructions. What does it mean here? So, where is the operand? So, operand is it A, directly A? No. And the operand's address is actually A, correct? So, I can say that here effective address is directly A, correct? So, this is the way we can understand. That means the operand is directly we have here. Sorry, operand address we have directly here. So, effective address is A. So, slowly you will understand. Example, if I have register indirect. In register indirect, what is effective address? Example, instruction of register indirect is load R1 into A, right? This kind of stuff. So, now, what is effective address? Is that effective address is A? No. So, effective address is for that, sorry, we don't write like this, right? We write like this, some other register. Already I told you, there are, of course, in some of the CISC instruction set architectures, so we write memory address also here. But in register indirect, this should be another register. Let us take R2. Okay. We don't specify here memory address, remember. That is memory indirect. Now, I am talking about register indirect. In that, this should be register. Now, effective address is register 2? No. That means, if I go to register 2, am I going to get address? I mean, I am going to get operand? No. Then effective address is not R2, but effective address is nothing but this one. So I use this symbol to say that you go to R2, then there is an address, take it, and again if you go to that address, that is the meaning of this one. So that's why then you get operand. That's why effective address is nothing but address which is in R2. Correct? That is effective address. Here in absolute addressing like load R1 something A, effective address is A. That means if you go to address A, you get the operand. Here if you go to address R2, you don't get operand, but you have to take that R2's value. That means you have to take that address and you have to go to that address, then you get the value. That is the difference between effective address here A and effective address here R2 in the braces, right? So that is about effective address. Now we'll see what is effective address in index register addressing mode also. Before that, let me explain you what is the purpose of index register addressing. Generally, we use this index register addressing especially for accessing arrays. Okay, that is one important idea. Example, you want to access a 2-dimensional array or 1-dimensional array, anything, then we can use this index register addressing mode. So, what is the syntax generally? I will tell you. So you will be writing index register addressing instructions like this. Load R1 X of something like this, R5. So here this is called, X of R5. This part right, indirect addressing. But if I add something extra offset, then that is called index register addressing mode. Here we are having an element called index. X can be treated as index. Okay. Now we will see an example. What is the purpose of this one? I will tell you. And whenever you write it like this, what is going to happen? So what is going to happen? And one more thing I have forgotten to tell you. So here, whenever I do X of R5, then the meaning of this one is adding X plus R5. Okay. So the content of R5 will be taken and that will be added to X plus R5. Okay. So that is the meaning of X of R5. That means here indirectly effective address is nothing but X plus R5. That is what I would like to tell you. So in index register addressing mode, the instruction looks like this. X of Ri. Okay. X of some Ri. When you write like this, then where is operand? If you want to know the operand address, that means effective address, if you want to know for that operand, that is X plus mod this suffix Ri. That means we should not add Ri to X. We have to add content of Ri to X to get the effective address. Okay. Similarly, base register addressing mode also you can understand. Now here actually there is an ambiguity I would like to resolve. So finally you understood index register addressing mode, right? So actually in theory, so different authors define them in a different ways. So but the high level idea is same. Finally you will have some index and some register, we have to add them. Okay, that is one thing. That means we will be adding two components, some register value and some integer. That is what the idea. But different authors define them in different way. So first we will try to understand according to Hamacher what is this index register addressing mode and what is base register addressing mode and PC relative mode. Of course, PC relative mode is same everywhere, but these two are ambiguously defined. Hamacher's idea is like this. There is only one addressing mode according to him, that is index addressing mode. That's it. Okay. Index register addressing mode, I can say. Index register addressing mode. In that we will be writing instructions like this. Load R1 and 20 of R2 like this. So here effective address of operand is nothing but 20 plus content of R2. That means like this. So this is about Hamacher's definition of base index register addressing mode we have studied. Now we will come to Starlings. Starlings defined them in a different way. So this idea also important for us sometimes. Okay. Just keep these things in your mind. That's it. Whenever some gate question is asked, based on the question, we can answer either you have to follow Hamacher or Starlings, you have to decide. Okay. And however, only one option will match. Such a way they give the question. But if according to ambiguity, if Hamacher's definition gives different answer, Starling's definition gives different answer, then we can't say anything because there is no unique literature here. No one can do anything. That's why keep all the aspects in your mind. Now Starlings, according to Starlings, index register addressing mode is what? We will see. So according to Starlings, index register addressing mode is like this. There is a register. That register is going to have some value. Let's call 20 or something, whatever. Otherwise, let's take 5. Now in the instruction, we are going to provide memory address like this. Example, load into register R2. So some memory A and R1. We write like this. Okay. So A of R1. This is what the syntax maybe. We can use like this. That means we are going to provide one memory address and we are going to take content of R1 which is 5 and we are going to add. Here you should know what is effective address. The effective address here is nothing but A plus value at R1. This is effective address. So when you follow this method where you are using some index in some register, that means we are using some index register and some memory address, then to get the operand address we have to add memory address and content of that register. Such addressing mode is called index register addressing mode. So here R1 is called index register, right? Now we'll see second one, base register addressing mode. In base register addressing mode, see concepts are same. but they define in different ways. So in base register addressing mode, you have base register instead of index register. So in base register, you are going to have memory address, some memory address, let's call 120. Okay, now your instruction will be like this: base register addressing mode, load into register R1, let's call this as register R1, this is R2. So load into R2 maybe. Now I am going to give the operand. So how you give operand, it defines addressing modes, correct? Now here I do like this. In this one, so we have already memory address in register, right? Now the displacement will be given in the instruction like this: x of R1. So where x is nothing but some number, maybe any number. You can use 20. So now what does it mean? Load R2 20 of R1 means we have to add first 20 plus content of R1. Same thing we did in the previous iteration also, please recall. So there is no difference actually, correct? That's why, so Hamacher also says same thing but in a different way. You should understand, you try to consolidate all these things. Now 20 plus R1. If you clearly want to differentiate index register addressing and base register addressing, this is the difference. What is that? In the index register addressing, we had index, that means some integer in the register, and memory in the instruction. Now in base register addressing, memory address is stored in register and the integer is explicitly mentioned in the instruction. See, 20 of R1, but both are same. So this is about Starlings definition and Hamacher. What I do is I follow Hamacher definition, hence I don't know what is base register addressing. According to Hamacher, there is only one addressing mode, which is index register addressing mode. Using that, we try to understand the things. Okay, but really time comes whenever really you have to differentiate base register addressing and index register addressing, use William Starlings definition. Now let me use that Hamacher's definition to understand index register addressing mode. Recall, what is that? So according to Hamacher, there is no concept of there is no particular register for integer or anything. So you can have anything. You can have a register with some memory address, something 200 generally. So according to Hamacher's idea is, in register we'll have some memory address and we'll be writing instruction like this: load x of R, okay, into some another register R5. Load R5 x of R here. This is, let's say, some R3, x of R3. This is a idea about Hamacher. So where x represents displacement. Okay. Now R3 is nothing but, see this one, right? Content of R3 is 200. Finally, what is the effective address here? Same story, x plus R3. According to Hamacher, you can write here memory address, otherwise integer also. You can give integer here like 3 and you can provide memory address in the instruction itself. Okay, so not a problem. So let us follow this idea and we try to implement one program. I will come to PC relative mode later, but now what we are going to understand is, we are going to understand how to write a code and what is the purpose of this index addressing mode or index register addressing mode. I will explain you. Example, let's say you have some students, n, 5 maybe. So student ID, so first memory location, already these values are loaded. Mr. Assembler already loaded, otherwise, so the loader loaded already the code, okay. Now n is value 5, there is student ID. Sir, what is student ID? Is it a text? No, it's not some number. Maybe you can assume it like one binary pattern which represents some number. So generally that is not really important for our code, okay. So maybe student ID 1. Now test 1. So test 1 contains some marks like 2. Test 2 contains 3, test 3. These are all the student ID 1's marks. Then student ID 2 got these marks 5, something, 7 and 9. In that way, there are a lot of students. What is our program's intention is, we have to add, we are going to have some more variables like, sum 1, sum 2, sum 3. I did not mention here, but I am showing here. 132, 136, 140, right? So there are 3 other variables, sum 1, okay, and sum 2 and sum 3. So here we have to store students marks, the aggregate of student marks. That means student 1, student 2, student 3, every student's test 1 mark should be added, every student's test 2 marks should be added, all the students test 3 marks should be together added, and we have to store in sum 3. Okay, that is what the program we have to write. For that, how to write it we will see. I am going to use index addressing mode. Okay, now index addressing mode, what I am going to do is, we'll see the details. First of all, the main idea. This is 5, right? That means we have to write a loop based on this value. So that's why let us first load it. Load that value into a register called R1. First register is going to have count number of students. So load R1 n, right? So we know that absolute mode. Next step is what? Then we have to take every student and we have to compute sum 1, sum 2, sum 3. We need 3 extra registers, correct? So let us take 3 extra registers. One is R2, another thing is R3 in that way. Let me take load R3. Sorry, not loading. We have to take 3 temporary registers, right? Clear them. That means make them to zeros first. Clear R2, clear R3, clear R4. Okay, now I have 4 registers. Okay, for simplicity I am taking 4, but with less also we can solve this problem, but for easy understanding I am taking 4 registers. This register contains count, number of students. We have 3 empty registers. Now what I am going to do is, so based on, I am going to write a loop now. Okay, so in the loop what I do is, I take every student's marks, test 1 marks, and I am going to add to R2, test 2 R3, test 3 R4. Then I will come to another student. Then I take test 1, test 2, test 3 marks and I add to R2, R3, R4 respectively. For that I have to write a code. I don't know how to write, but I am just thinking. Okay. So meanwhile you also think about it. So how to write it? For that, what is my idea is, somehow first I come here. Then I do the desired task. That means I add 2 to here, 3 to here, 4 to here. Then I will come here somehow. Then again then I have to come here. Okay, that means I have to jump from here to here. Then again I have to do the same stuff. Yes, now there is a repetitive stuff. First we try to understand that repetitive stuff. What is that? Example, initially you are here. Then how to add this one and this one and this one to R2, R3, R4. We'll do like this. First of all, are you here? Where is this address? Correct? List. So assume that the variable name is list like n. Then let me load that into another register called R5. So R5 contains list. Okay. But I want I want this address. I don't want content. So that's why I use immediate mode. So by this time you should get experience. Already we have seen how to use this hash, how to use this address and how to increment it, correct? Slowly you will understand. The first step is, now R5 contains, first of all we see the contents. R1, R2, R3, correct? So R1 is having initially 5. That means there are 5 students. Next R2, R3, R4 contains zeros, correct? We cleared them. Then started taking list value. That means immediate mode. What is list? 100, right? We are storing now that 100 into register R5. R5 contains the initial memory address. Through this we have to access this. So I use index register addressing mode. Here you see how. The first step is add, correct? I want to add what? This value to R2. But for that we have to fetch it, right? Already I told you in my risk instruction set, at a time I can't add and I can't fetch the data from the memory, right? For that, let me fetch them into load. Let us use another register, not a problem. Another set R6 into R6, this one. How to fetch it? Already I told you. Now index register addressing mode we can use. So in index register addressing mode, we have what now? R5 contains the address, right? This one. You tell me, what is 104 with respect to 100? 100 plus 4, correct? Then I use like this. So like this, otherwise like this. In that, I am going to write 4 of, what is that register? R5. R5 contains 100. Because of this addressing mode, what happens already? This is now index addressing mode. In that, R5 contains 100. 100 plus 4, 104. So directly we go to 104. So what is effective address of operand? Recall. In this addressing mode, effective address is nothing but content of R5, 100 plus 4, 104. Effective address 104. Then go and fetch the data. So that is test 1 marks. Perfect. So R6 is going to, let me use R6 here. Now R7 here. we are going to use R7, R8 also. You will understand it slowly. So R5, R6, R6, R7, R8. So in R6, I will be, loading what? 4 of R5. Now, in R7, what I do is, I load 8 of R5. Try to understand what happens if I use 8 of R5. So here R5's content is not modified. Remember, we are just using it. I am not modifying R5. So 4 plus R5, 8 plus R5. So what is 8 plus R5? What is R5? Still 100, right? So 100 plus 8, 108. That means test 2 marks. So we are loading into R7. Similarly, load test 3 marks into R8. Okay, 12 of R5. So this is the usage of index addressing mode. Happy. So when you do it, then we'll get marks of test student 1, test 1, test 2, test 3 marks into R6, R7, R8. Then I use adding. Okay, add R6 comma dash. So we have to add R2, right? We have R2 initially. Add R2 equal to R2 plus R6. Next, try to understand. Then add R3 equal to R3 plus R7, right? Small mistake here. R6, R7, R8. Correct. R6, R7 and add into register R4. R4 plus R8. In that way. So R6, R7, R8 contains what? Recall. See these 3 steps, because we loaded 4 plus R5, 8 plus R5, 8, 12 plus R5. Then these 3 marks will be added here. 2, 3, 4. Then these 3 steps if you focus, then what is going to happen? R2 equal to R2 plus R6. 2 plus 2, 4. Sorry, 0 plus 2, 2. Then R3 equal to R3 plus R7. R3 is 0. 0 plus 3, 3. Similarly, R4 gets what? 4. Correct? Now once it is done, we should go back. How many times you have to do? For that we are going to write an instruction called branch instruction. Branch if we have to branch on what? What is that register? Recall R1. Branch on R1. If that is greater than 0, then only we should do all this stuff. From where? From here. Correct? So I write here loop. But unfortunately, the problem is every time we will be fixing R5. Correct? Then you get same addition. Every time we should not do the same stuff. Next time when you go to loop, then this first time we started with respect to this, we took these 3 values, right? Next time the list value, that means we should come somehow to here. When I come to here, then if I do the same thing, that means next time finally what I want to tell you is this 4 plus R5, 8 plus R5, 12 plus R5 should refer these 3. For that R5 should come here. So where is R5? Here, right? So you loaded R5 with list, right? Then here, so after coming here, before going back to the loop, what we do is we add extra step which increments our R5 so that R5 comes to this point, student ID 2, right? So for that, let me remove this branch. Here I write add that R5 equal to R5 plus 16. If I do that, so initially R5 is 100, next time it will become 116. So it will point this one and the remaining story is same. So you can understand, not a problem. Here I write branch if R1 greater than 0, then go to loop, right? So loop is nothing but this instruction, right? Now we will see whether it works or not. So once it is done, second time when you go back, since R1's content is what? See, R1's content. And one more thing. So when you do one iteration, we should reduce this R1 value. For that, somewhere here we can write subtraction, right? So subtract R1 equal to R1 minus 4. That means R1 hash 4. Sorry, not hash 4, hash 1, right? So hash 1. If you do that, then R1 will become 4, right? Now number of students to be added is 4. Now go back to the loop, load R6 with 4 of R5. This time 4 of R5. What is R5? 116. 116 plus 4, 120. Then 8 plus R5, 124. 12 plus R5, 128. So these 3 things will be taken into R6, R7, R8. So what are they? R6, R7, R8 contains now these 3 values. They are 5, 7, 9, right? So once they have been taken, then we will be doing these 3 steps. Add the two R2, R3, R4 respectively. R6, R7, R8 will be added to R2, R3, R4. Then these will be added. 2 plus 7, 9, 3 plus 9, 12, 4 plus 9, 13. Then again subtract R1 equal to R1 minus 1. Then this will become 3. Now add R5 equal to R5 plus 16. This time your next student will be taken. In that way this will work. In that one the driving point is index addressing mode, correct? So I can say finally, if you assume this data as array, correct, in high level C programming, you will be having a 2-dimensional array, that is nothing but some set of students and marks, correct? Student 1 his marks, student 2 his marks, like this. Otherwise structure, even structures also can be implemented. Finally either arrays or structures can be easily implemented using index addressing mode, correct? So that is the advantage, right? Now finally you successfully understood various addressing modes, right, through the code. Sir, why are you teaching these lengthy codes? We didn't understand. Why don't you directly tell that this is index addressing mode and this is the functionality? When you write this kind of code, then you can understand the necessity of each and every addressing mode. Okay, so while writing the code, slowly you understood why we use absolute addressing mode, why we use register addressing mode, right? So many stuff. If you don't know that, if you don't write the code, then it will be like remembering the details. Then in the GATE exam, if they ask a question related to addressing mode, if example like this, what is the purpose of index addressing mode? They give 4 options. Then if you don't have experience of writing the code like this, at least you have never seen the code, then you can't easily interpret that kind of addressing modes and their necessity, correct? That's why I'm explaining the concept through the program, so that you can remember them for long period. Okay, so this is about this index addressing mode. Now we'll see PC relative mode. What is it, sir? So in PC relative mode, generally what exactly the story is same. There will be a program counter, you know that, right? So program counter, and we will be only telling the displacement, and program counter, that means the index register is, otherwise the base register is fixed. Okay, now only we tell displacement. Example like this, jump instruction. So far I did not teach you jump instruction, right? There are some instructions called jump instructions we use in this assembly level programming. So that purpose of jump instruction is directly like go to. Okay, so we jump to some instruction. Okay, so for that we will be mentioning the address part here. Now example, if I say here jump to 4, so what does it mean? 4 means what? So here if it is in PC relative mode, then the address to which we have to jump is 4 plus program counter. So but you did not mention program counter in the instruction. Yes, I don't mention, but it is implicit. So finally, if your processor knows that this jump instruction is representing PC relative mode, then automatically what happens? Program counter will be added to that displacement. In that way, so we can easily implement PC relative mode addressing modes. Okay, blindly remember one thing, automatically whatever the displacement you mention in the instruction, like jump 4 maybe, then that value will be added to the program counter to go to the next instruction. Understand? Now remember one thing, generally program counter will be automatically incremented while executing your instruction, right? Example, let's say your instruction executing instruction 1, then program counter will be automatically incremented. But remember one thing, when you have this kind of instructions, program counter is not incremented. Program counter will be updated with this one. Okay, so here jump 4 means what? I will tell you with example. Example, program counter contains 200. If it is not branch instruction like this, okay, let's say if it is simply add stuff, add something. When you execute this instruction, while executing this instruction, program counter is 200. Once this instruction is executed, eventually this program counter will become 204. That means next word, it points to next word, so that next instruction can be taken, right? So that is important. Otherwise, how can you access the next instruction? So we know that generally we write program such a way that should be executed line by line. That means word by instruction by instruction. So that's why program counter should be automatically incremented while executing your instruction. Generally that happens. Okay, but exactly we don't know when. But in the execution phase, already I told you, instruction execution contains two phases, like instruction I can say evaluation. One is fetching, correct? We have to take the instruction and we should understand what it is. Without that, directly can we guess that it is addition instruction, right? So first of all we have to take that instruction from the memory, then we have to decode it, correct? Then we should understand, don't worry. So I have not discussed what is how to do all that stuff, right? I will be clearly teaching that in pipelining, don't worry. Here I am just giving rough idea how your computer works. Your processor takes instruction and it fetches it, then it decodes it. That means it executes it, okay? Let us take only two phases, but generally it will be done in multiple phases. If I have to divide into two parts, I divide into two parts. Fetch, take it, execute it. Now while executing your instruction, once it is done, we should go to next instruction. That's why for that convenience, program counter will be incremented by 1 while executing the previous instruction. Okay. But if there is a branch instruction like jump to, let's say it is not PC relative mode, directly we are mentioning the address, let's say, okay. Forget about PC relative mode. If it is just normal addressing mode, absolute addressing mode, we mention the address jump to A. Otherwise, let's say there is an instruction called jump to 500. Whenever I write this kind of instruction, that means we have to go to 500. In this step, for this kind of instructions, program counter will not be incremented, but program counter will be updated to 500 while executing this jump instruction, okay. That is the difference. That's why don't blindly remember that program counter is automatically always incremented. Yes, it's always incremented unless, if the instruction is not this kind of jump instruction or branch instruction. Example here also. So in branch instruction, did you remember? We went back to another, we went back to initial previous code, correct or not? For that, program counter should not be incremented, correct? Of course, in C programming also, you know that. So how generally program will work? We execute line 1, line 2, line 3, line 4. Suddenly if there is a condition or sometimes if there is a loop, then we'll come back, right? In the same way, so program counter generally will help you in sequencing the program execution. We execute like this, line 1, line 2, line 3. That's why program counter should be incremented by 4. Suddenly when there is a branch instruction, program counter should be updated in a way though so that we can go to the right position which is mentioned in the jump instruction, okay, or branch instruction, whatever it is. So this is about general scenario. Now we'll see PC relative mode. In PC relative mode, instruction will be such a way that there is a implicit register called program counter. Now example is jump instruction. If I write here jump of x, then for effective address of here operand is x. So this operand, so where to go now? The purpose of jump instruction is we have to go to one address. Where is the address? Address is PC plus x. Okay, remember it. So this is the idea about PC relative addressing mode. Okay, so blindly remember one thing. So program counter, that means your instruction, otherwise the jump is related to your program counter. Okay, that means finally program counter's value will be taken into the consideration while calculation of this address, okay. That is about PC relative mode. Sir, what is the purpose? Why we want to use PC relative mode? So here effective address is what finally in PC relative mode? That program counter plus displacement, correct? Remember it. So program counter's value plus displacement, right? But this is not compulsory to give in the address, instruction. In the instruction we don't mention PC, but generally we mention it, correct? So but in index addressing mode and base addressing mode, we mention displacement and the corresponding index or base register in the instruction itself. But here in PC relative mode, that program counter is implicit. It should be automatically added whether we mention it or not. So that is about PC relative mode. Sir, but why we use it? What is the purpose? Example, let's say you are writing a code with respect to where all the address instructions are in PC relative mode. Okay, that means what? Example, there is a jump instruction. So that jump instruction is written with what idea? That means we are jumping to, example, let's say currently your program counter shows 100. Jump 4 means what? We have to jump to 104. That means the control goes to 104's memory location. Right. Why we have to write this kind of code? When you write this kind of code, then suddenly if I start my program and if I execute my program in a different way, I will tell you the reason. For that, let me erase this mode. Now, to understand PC relative addressing mode's benefit, you should understand one concept called position independent code and position dependent code. So this is all the story at 1960s. So in 1916s, the idea of execution was different. Okay, now we have modern architectures and modern operating systems. Now we are executing the codes in a different way. So what was the execution model? We will see at that time. So at that time, the idea was like this. So people used to write programs. Okay, now whatever the language they use doesn't matter. So mostly they use assembly level programming and assume that finally it is converted to machine instructions. Okay. Now once this program is converted to machine instructions like this, I1, I2, I3 followed by this is data that program is requiring. Okay, like we have seen just now, right? Now, so there will be some typical instructions like this: load maybe register R1 into some memory location A. What does it mean? We have to load content of A into R1. What is A? So A is nothing but one of the memory data item. Here though you are writing A, but in the machine instruction A is nothing but maybe some data at memory location 100. Correct? Now you have such kind of instructions. Sometimes you are accessing memory address 100 and we are taking the data. Such a way you have a program number 1. Now it is ready for execution. Then we load it as it is. So we load, assume that let's say we are loading that program from 0 to 100, where first 0 to some 10 are instructions. Remaining thing is data, whatever, doesn't matter. We don't go into details. But what if another program wants to execute? We will see what happens. If another program wants to execute, then that is also converted to machine instructions, right? Then that program is also going to have write instructions like this. For that also, let's say memory addresses, right? What if this program has this instruction load A R3? Okay, sorry, load R3 comma something B. According to this program, B is nothing but memory location 70, but currently 70 memory location is using by this program number 1, right? There is a conflict. Program number 2 also written with same idea, like we know this program number 2 is also using memory address 70, but program number 1 also may be referring 70, right? Then can you execute now? You can't execute, even you can't load it, because this program is designed such a way that this program also wants to occupy here. Then we say that this kind of programs are, these kind of codes are position dependent codes. So we are fixing the memory addresses. We want to keep our data into 100. Then this program only works if you have memory location 100 with you, right? We can't give that 100 to others. So that's the problem. Such kind of codes are called position dependent codes. But nowadays there is no such problem, because so though you write whatever the program you write, so whatever the physical address, we directly don't specify physical address nowadays. So in 1960s, so programs are written in this way, but now you can't understand everything at a moment here, because so I'm using a concept of operating system. In operating system we have virtual memory, right? That means you write a program such a way that, and you feel that you are using memory addresses like 0, 1, 2, they are not real addresses. They will be mapped to some physical addresses, not particular physical addresses. When there was no virtual memory concept, then people used to write programs with absolute addresses and absolute addressing mode. Example, let's say your instruction is like this: I want to load data from memory address 100. This is absolute addressing mode instruction. Then we are absolutely fixing the memory address, and you are saying that I want 100. Then in that scenario, then multiple programs cannot run at a time, correct? So that is a problem. If program 1 runs, until program 1 is finished, we can't execute program number 2. So at that time, so there was a necessity of writing position independent codes. That means somehow you have to write a code such a way that you should not refer any memory address directly. We should always refer data indirectly. When you do that, what happens? Example, let's say if you write PC relative data, everything PC relative. That means your instruction will be like this. So wherever I am, so whatever my program counter is showing, for example 80, then I want 80 plus 5 data. I want to refer 80 plus 5. I want to refer 80 plus 10, and I want to jump to 80 plus 30. In that way, if you write the code, then these values are not absolute, right? They are relative to your program counter. Now you see, then what I do is, such kind of program is not specifying any particular addresses. It is not rigid about memory locations. Now we can ask Mr. Program number 2, my dear program number 2, you never used any absolute address, correct? Then can I load you in starting address of 500? Okay. Then it says yes. Okay. Now whatever you refer, so from now onwards this program is going to refer any data which is absolutely with respect to program counter. So that's why now from now onwards we never touch this program, right? Our access will be like this: 500, 500 plus 10, 500 plus 20. If the same program is loaded from 200, then the idea will be like this: 200, 200 plus 10, 200 plus 20, in that way. So without touching program number 1, we can we can execute our program. So such kind of programs are called position independent programs. Okay, we can write it, not a problem. So never use this word, I want memory address 70. Okay, if you don't write that kind of instructions, then that code will become position independent code, but nowadays it is not required because of virtual memory. So automatically everyone is having our own address space. Okay, so every program can write its own code, like it can say directly, I want memory address 0, but your operating system is going to take care of all that stuff. So it is going to give you a feel that you are accessing memory address 0. Such a you are writing code, but your program will be executed some around here at memory address 1000, but still your program will be properly executed. Okay, there are a lot of advancements you can understand only when you discuss operating system and memory management of operating system. Here of course our intention is different, right? We are learning addressing modes. So that's why just brief idea of this PC relative addressing mode is important. So using PC relative addressing mode, I write all my instructions with respect to program counter. Okay, whatever I want to access, I say PC plus 7 I want to access. Load PC plus 7. Fetch, store PC plus 10. Jump to PC plus 20. Then we never use absolute addresses. That will be position independent code. Nowadays it is not required. Now in the GATE exam, so many times they ask this question: what is the usage of PC relative addressing mode? Then definitely to write relocatable code, correct? So that means we can move our program from here. We can run this program here for some time, then we can move it. That means we can relocate it. It's not rigid, like it's not fixed code, right? That means it is not compulsory to execute that program in a particular place. We can relocate it. That means tomorrow we can execute that program from here, maybe from here, day after tomorrow, next time here. So such kind of programs are called relocatable code. Okay, now, so that is about PC relative addressing. So many addressing modes we are studying. Now we'll see the summary of all these addressing modes, whatever you have learned. Now what is the purpose of indirect addressing mode? Generally we can use indirect addressing mode for implementing pointers. Okay, I will explain with one example. So why we can implement pointers using indirect addressing mode, I will explain with one instruction. Okay, example, let's say you have C programming instruction like this: A equal to star B. Okay, now to have same idea, like finally what is the meaning of A equal to star B, we will see. A is a memory location, correct? We assume that it is here. Now B is another memory location, B. Okay, A is 100, B is 200. So finally A equal to star B means we have to write value at B. B is, let's say, having a memory address 100. So star, go to C programming. In C programming, B means 100. Star 100 means what? Value at 100. Value at memory address 100. Let's say this is 5. Okay. So we are writing A equal to star B. We do one thing. We take another variable C, but I don't show in the instruction. To understand it in easy way, 200 contains 300. 300 is C. 300 contains a value 7. When you do A equal to star B, since B is having 300, star 300 is what? 7, right? So finally A should get 7. Here we should get 7. For that we have to write instructions. See how to write it. Try to use assembly level programming now. First step. If you want to fetch this data, first you should know where is B, right? So assume that I know B, correct? So I load B into register R1. Okay, B. Next. So now recall. Load R1 B means R1 contains a memory address B. Yes, it is possible for us using RISC architecture, correct? This is absolute addressing mode. So B is what? B is 300, right? Yeah. Now next step. Load into register R2, which is nothing but R1. Try to understand this one. Is it not register indirect mode? Yes. So what is the meaning of this one? R1 contains something. So go to that memory location. That means R1 is 300. Value at 300. Go to 300. You get some data. Fetch it, correct? And of course, so when you do that, so directly we fetch what? 7 into R2. Now R2 gets what? 7. What is our target? We have to store it in A. For that we do like this. Store into A what? R2. Store R2 comma A. That's it. Then using these three instructions we can implement A equal to star B, isn't it? So that means pointers can be implemented using this. What is this addressing mode? Register indirect addressing mode, correct? So finally indirect addressing mode. Now already we have seen index register addressing mode. Using index register addressing mode, so we would be able to implement what? Arrays, right? So we can access arrays and lists, right? Structures, anything. Index registers. So that is index register addressing mode. Now what is the benefit of one more thing, like we have covered now, PC relative mode. So what is this PC relative addressing mode's advantage? So we can write positional independent code, correct? So these are all the details about addressing modes. If you know this stuff, you can answer anything, but still I will be covering some more details. Like in C programming, what are the things you do? You sometimes write programs with functions, right? That means we call a function and then how that function is executed. I already told you one thing. When you write a C program, then that C program will be converted to machine level program, correct? Now in the machine level, if you don't have support, machine here means assembly level for me, okay? But there is no difference much difference between assembly and machine, you know that, right? Now here, so C program is converted to assembly. Then if there is no assembly instruction which supports C programming, I can say C programming ideas, then we can't implement, right? That's why. So definitely you are executing one C programming in one machine means whatever you are doing with C program, same thing should be done using assembly level. Maybe you require more instructions. Example, when you are doing A equal to star B in C programming means your compiler is going to convert this kind of instructions. Compiler means here assembler, okay? So assembler should convert like this, otherwise it is not possible, right? So that is one thing. And one more thing, so I have forgotten to tell you, this PC relative addressing, people used to write this kind of PC relative addressing mode instructions to develop the compilers, okay? So that compiler can be executed from any position. I was talking about the older compilers, okay? Nowadays you can implement without PC relative addressing also, not a problem. But this entire story was about 1960s, okay? Now we can write sophisticated code with other addressing modes also, not a problem. This is not compulsory, but in the GATE exam they are asking such kind of questions. That's why I would like to add that point. Now, so finally in C program you have functions, correct? We'll see how these functions can be implemented. You should get some confidence. You got some confidence that pointers can be implemented, right? Similarly double pointer, triple pointer also can be implemented, okay? So using same model we can implement double pointer, triple pointer also. Think about it. Now what I would like to talk about is how this function can be implemented. What's the problem with function? Is it not straightforward, sir? No. When you execute a function, then we are moving. That means your program counter should be changed from one position to another position, correct? It is like a branch instruction. So example, you are executing at 100, suddenly you have to go to 200. Then the real problem comes. once the work is done, we should come back, right? That means we have to come back to next instruction where you were when you are calling that function, correct? So example, let's say you are executing some, let's say you are calling this function in C programming. After that there is a next line, okay, next line. So because of this call, we should go to that function and we have to complete that job, and we have to come back to next line. So how it can be done using assembly level programming, we will see, okay.